So for this question here, we're looking at which interval has the smallest rate of change. So we're looking at from -2 to -1, -1 0, 0 to 1, and from 1 to 2. I guess my first step here would just kind of be to look at the graph. Notice that we have from left to right, it's slowing down really, really fast. So we can see like, okay, from 2 to 1, we have like a really fast rate of change. From -1 to 0, a little bit slower. 0 to 1, even a little bit slower, and then from 1 to 2, it's still the slowest. So for here, I would have to put D, just for that reason. Next question is fill in the blank. If f of A is equal to f of B, the average rate of change of f on the interval A to B, here that's going to be 0. We can show that because the average rate of change will be f of B minus f of A over B minus A. But here we know that f of A is equal to f of B. So we can just go ahead and say that 0, or if we wanted to, we write in, okay, well, instead of f of B, let's write f of A minus f of A over B minus A. Again, 0. So we know the whole rate of change has to be 0. Moving on to section 1.3, graph some rates of change. So for each of the following A through E, we need to figure out the answer from f. So here, 16 f of b, b just goes right up to r, so we know that f of b is equal to r. Next question is f of x is equal to r. Notice how we have we drag r over, lines up with b, but also lines up with d. So here we would have x, b, and d are possible solutions. Next, we need to solve for f of x equals 0. If we notice on our x-axis here, our function never really passes through that. So we know that that does not exist. There's no value of x for that to be the case. And then our next question is finding the intervals on which f is increasing. We just kind of look here. That's about where we have our trough. Everything up to that is decreasing. Everything after that, increasing. So the way that I'm going to write this is just saying, okay, well, at C, we know the derivative is 0, so we're not going to include that. So we're going from C on, again, C is not included, up to, say, positive infinity, just because that looks like a parabola. And now is the average rate of change on the interval, C, D, positive, negative, or 0. I'm going to go ahead and erase everything we have here. There we go. So looking at C here, up to D, we can see that that is increasing, so it is positive. So the average rate of change from C to D is positive because the function increases. To the right. Now is f of d minus f of b positive, or f of d minus f of b over d minus b positive, negative, or 0? So if we notice, that is the same equation that we have for the average rate of change. So let's look at the average rate of change from b to d. If we notice, like we said earlier, f of b and f of d are both equal to r. So here we know that f of d is r minus f of b is r over d minus b is equal to 0. So therefore, therefore this expression is equal to 0. Okay, now for problem 17, we have if f is a decreasing function, then which is the largest? Explain. So if f is a decreasing function, then that means as x increases, then f will always be decreasing or staying the same. And I guess we just really want to focus on the fact that it is decreasing, or like at the very best, it's staying exactly the same. So if we think about it, we're going from -8 to -1 to 0 to 3 to 10 and our x values, right? So as we're increasing in x from -8 up to 10, f will be decreasing, 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 decreasing. So that means that a, f of -8, is going to be the largest. Okay, so next, problem 18, we have find the intervals at which the function is increasing or decreasing using interval notation. So looking at our function, we can see that at -3 and -1, we have a local maximum, a local max, and a local min on our curve. So those are going to kind of serve as the breakpoints for where we have where we're changing from increasing to decreasing. So we're increasing, as you can see, from -3 up to 1. Let me change the color real quick. From -3 up to 1, you see that we're increasing. And now those maximum and the minimum, those are not going to be included on that interval. So we have from -3 to -1, not including our endpoints. Additionally, after that, we're decreasing up to our minimum, and then we're decreasing again after our maximum. So we're going to have two sets. We're going to have two intervals. We're going to go from -infinity to -3. Again, -3 is not included, and we can never include infinity. We're going to have a union from -1 up to infinity. Now, problem 19, we have sketch a graph with domain -4 to -8 that has a negative rate of change on the interval from -4 to 2, a positive rate of change on the interval from 2 to 8. So I guess the way that I'm going to draw this, I'm going to draw my curve. I'm going to draw my axes real quick. The x, we go up to 8, down to -4, but -2, 2, 4, 6. So from our interval, we know that we're decreasing down to x of 2, or x is 2, so I'm just going to mark that here. And we're increasing from 2 to 8, so maybe that looks like this. And we're decreasing from -4 to 2, so I'm just going to kind of draw that like this. And now, I guess it's important to note that we don't really want to have arrows on the ends because we know the interval. So I'm going to write it like, just kind of draw a dotted line here. Next, we have that the tangent line at x equals 4 to our graph passes through the points 4, f of 4, and 0, -5. So you want to find the rate of change of f at x equals 4. Something, I guess, cool about our tangent line is that it's going to have the same rate of change throughout. So from here to here, the rate of change is going to be the same as our function at that point. So I guess first it's important to know, or first it's important to evaluate what is f of 4. So that would look like f of 4 equals -1 over 2 x minus 5 squared plus 4. Okay. Instead of x, we're going to have 4. There we go. So we'll have -1/2 times 4 minus 5 is -1 squared plus 4. And that will be equal to -1/2, because -1 squared is 1 plus 4, and that will be 3.5. So we know what this point is here now. We know that that is 3.5. And we know that this is 0, -0.5. So if we think about it, we can determine that rate of change of this line between those 2 points and that would be the same as the rate of change of our function at the point of intersection here. So let us draw that out real quick, or let's determine that. So that is going to look like f of 4 minus f of 0 over 4 minus 0. Now, like we did earlier, we already know that f of 4 is 3.5 minus, our question gives us that f of 0 is negative 0.5. Whole thing over 4 minus 0. Now 3.5 minus negative 0.5, that's just the same as 4. 4 minus 0 is the same as 4. So then our average rate of change is 1. So let me write that out. Rate of change equals 1. Okay, so next for question 21, we're looking at this graph. We want to look at the function g with domain from negative 2 to 7. We're going to find each of the following using interval notation. So if we're looking at increasing intervals, we're going to want to point out the local maximum, the local minimum, negative 1 and 4. So we can tell we're increasing from here to here, and then from here to here. So we're going from, so on our curve, we're going from negative 2 to negative 1. Now, we already know that our local maximum is not going to be included, but because this is on an interval, we also are not going to include our endpoints. And then we're going to include a union from 4 up to 7. 4, again, local minimum, so it's not going to be included. And since 7 is an endpoint, that will not be included either. Now we have decreasing intervals. We know that we're going down on this entire range here, right? So that is going to be from negative 1 up to 4, which, again, since those are extreme values, those are not going to be included either. Now, we are going to look at our local maximum. That is going to be here at this point, because we can see from either side, we're going up to it, we're going up to it, we're going up to it, and then that is the maximum value that we're going to achieve. So that is going to be a value of 4.3. 4.3 at x equal to negative 1. And then we have a local minimum here with a value of negative 8.2. Negative 8.2 at the point x equals 4. Now further, we want to look at the absolute maximum and the absolute minimum. Now to do that, those can be inclusive of our extreme values, but they can also include our endpoints. Really just any point along the domain that could fall under one of those. So if we look at our absolute highest value, it's here up at 7, which has a value of 10.7 at x is equal to 7. Then our absolute minimum, again, is just 4. X equals 4, value of negative 8.2. Now here for 22, we're to assume that the graph has a domain from negative infinity to positive infinity, and all of the relevant features are shown to us. So for this first one, using interval notation, we want to estimate the x intervals where the graph is increasing and concave down. So looking at our graph, we can kind of see, okay, well, this is the area where everything is concave down just because it's opening down. And it's increasing up to this point. Right, so that's at negative 2. So we're going all the way from negative infinity to negative 2. Negative infinity not included, and negative 2 not included. Then we must see where we're decreasing in concave up. So concave up is going to look like this here. And looks like we're decreasing around from here to -3. So that'll be from -1, or sorry, from -1 to 0 here. So decreasing in concave up is going to be from -1 to 0, both of those unincluded. Now, next step is that we want to find the local maximum and or the minimum. So the local maximum here, right, that's happening at x equals 2. Sorry, x equals -2. A value of 7. Looking at our graph again, we have a local minimum at x equals 0, and that has a value of 3. Now, what is the approximate x value of the inflection point? That's going to happen between our maximum and our minimum. I guess from my perspective, it just looks like that's happening at here at x equals -1. So that's what I'm going to use. X equals -1. Perfect. Now for question 23, we want to consider a function f that has a domain of all real numbers. So we know that the graph is going to have a negative rate of change on this interval. It's positive between those two. It's concave up here and concave down here. Okay, so I guess first I'm going to focus on that negative rate of change. We know that during that whole time, we're going to be concave up. So that's how I'm going to draw that. So let's say we have our graph that looks like that. Axes here. We're going to have 3, 4, and 5 marked. So we know our function is going to be negative from -infinity up to 3. So I'm just going to kind of draw a point here and trace that up, which again we know is concave up because of our third statement. It's going to be positive from 3 to 5. In between 3 and 5, we're going to have our point of inflection. So that is going to kind of look like this. Let me get that a little bit smaller. It's going to kind of look like this. And then from 5 on to infinity, we're going to be decreasing again. So I'm just going to kind of draw that like this. And here, it's concave down, it's concave up. Looks good. For 24, we have true or false. The function f is decreasing. F is decreasing and its graph is concave up. Then the rates of change of f are negative. Rates of change of f are negative. They're getting larger when moving from left to right along the graph. Okay. So, if I were to draw a function that looks concave down or concave up, it is decreasing. So let's look at just kind of this. So it's decreasing, it's concave up, work on those. We need to look at the rates of change of f are negative. Well, for f to be decreasing, this has to be the case. So this is automatically true. And the rates of change of f are getting larger from left to right. So here we can tell it's very steep negative, right? So we're decreasing very quickly here. And as we move from left to right, our tangent lines are getting less and less steep. So that makes sense to me. We have really negative, very negative over here. A little bit less negative or more. A little bit more positive, a little bit more positive. So that makes sense to me. That seems true. Now finally for question 25, We have, suppose a function f has average rates of change as shown in the table, and you know that it is either concave up or concave down on its entire domain. So we have our x interval here, we have 2 to 0, 0 to 2, so on and so forth. Now which of the following graphs could be the graph of f? We need to explain. So something first that I want to point out is that our rate of change from the table, always less than 0. So our rate of change is less than 0 on domain. That means our function is decreasing. This graph here is increasing on the domain. This one and this one are decreasing though. So those ones are potential answers here that we could use. So I'm just going to kind of draw a red X over this and say, no. Moving on, we know that from negative 1.5, average rate of change from negative 2 to 0. Now from 0 to 2, we have negative 0.38. If we notice that rate of change is increasing, our rate of change really only tends to increase whenever we are concave up. So because we know that we're decreasing and concave up, B has to be the graph.